Hello, everyone. In this video, we're going to begin section 6.3 in our workbook on density and mass. So this section continues the theme of looking at applications of integrals. So we're going to start in this section by looking at an application in physics related to density and mass. So before we begin our first example, I just want to say a couple comments about what density and mass are. So you probably have seen these words, maybe if you've taken a physics class or an engineering class, you might have a strong notion for what they are, or maybe these words are kind of new to you. But let's start with mass. So mass tells us essentially how much matter an object contains. And we see mass in our units in terms of weight. So weight is a calculation that deals with, or where mass is used to calculate weight. So we can kind of view mass as a quantity representing the amount of matter a particle takes up. And again, we can kind of equate it to weight, and that if someone has, or an object has a larger weight, then it also has a larger mass if we're dealing with normal conditions like on the surface of Earth. Okay, so not super complicated. You probably already have a really robust intuition about what mass is. And density is a rate that deals with mass. So density is a mass per unit. So if our object is a one-dimensional object, say maybe a rod, which we'll meet in our section here, then density of this rod is going to be mass over length, over a length unit. So that might look like grams per centimeter. If our object is two-dimensional, like a surface, then the density is a mass over an area. So maybe population or people per square meter or square mile, maybe. So you've probably seen this on like population density of a town. But we also can consider density of a 3D object, in which case we have mass over volume. And so that could look like something like kilograms per meter cubed. Okay. And so the type of, or in the context that we look at, we'll be given the appropriate density to match the type of dimension of the object. Okay, so that's just a little background. Let's get started by looking at example 1, and this will start to make a bit more sense as we see more examples. So in example 1, we're considering a thin rod of length 10 centimeters. So we should think of this rod as a one-dimensional object. So we'll even draw it here. Okay, here's our rod. It has a length of 10 centimeters. Okay, so part A says find the mass of the rod if it has a uniform density of 5 grams per centimeter. So rho, the density, is 5 grams per every 1 centimeter. So uniform means that the density is consistent throughout the rod. So it doesn't get heavier on one end or the other. If we take any centimeter of this rod, it's going to be 5 grams. Okay, so then we want to know the mass of this rod. So because density is a rate of mass per unit, in order to find the mass, we can just calculate the total length by the density. And again, we're using length here because we have a one-dimensional object, 1D object. Okay, so for us, what does that look like? Well, our length is 10 centimeters. Our density is 5 grams per each centimeter. So then our total mass is going to be 50, 10 times 5 over 1. And we see here that the centimeters cancel, and so our units are grams, which is a mass measurement. mass unit. Okay, cool, not so bad. So why do we need calculus to compute such values? Well, density is not always as simple as example 1. We don't always have uniform density. In some cases, the density changes as we vary across an object, which is the case in example 1, part B. So example 1, part B says, find the mass of a rod if its density is given by a function of x. So the density at x is x over 2 grams per centimeter, where x is the distance from the left side of the rod in centimeters. So if we draw our picture here, I have our rod. So it's still going to be 10 centimeters. But we see that at this end, so when x is equal to 10, density at 10 is going to be 10 over 2, which is 5 grams per centimeter. But over here, when x equals 1, the density is going to be 1 over 2 grams per centimeter. So we're going to start with a fairly light rod here, 0.5 gram per centimeter. And then as we move over, we're going to get heavier at the end. So this rod does not have uniform density throughout. So if we want to get a different picture here, so if we measure over from this left side, if we measure over x, then the density here is going to be rho of x. Okay, so what we can do is take a little slice of this rod. So I'm going to take a little slice at x. Take this slice here. So I have a slice of rod. And I'm going to take such a small slice. I'll call this thickness, delta x, change of x. It's going to be so small that this little slice is practically uniform. So it practically has uniform density in this whole little tiny slice. So this whole slice has the same density. And that density is equal to rho of x. Okay, so then what about the mass of just that one slice? Well, the mass of the slice then is going to be about equal to, I'll use approximately, the length of that slice times the density of that slice. So length is delta x, and density is rho of x. Okay, so that is, again, the mass of just the little slice. But we want the mass of the entire rod. Mass of rod. So how do we do that? But we need to add up all of these delta x times rho of x. But we need to vary this x from 0, the beginning of our rod, all the way through 10. So when we're taking a sum like this is equivalent to taking an integral. Well, we're adding up the density, or the mass rather, of each little slice. So to get the mass of the rod, exactly, we're going to take an integral of these rho of x dx, using the notation of an integral. And we want that x, that length from the left side, to go from 0 to 10. So what does that look like in our case? Well, rho of x for us, I'll change color here so we can see exactly what it looks like for us. Rho of x is that x over 2. So we're going to have the integral from 0 to 10 of x over 2 dx. Okay, so now I just need to compute this integral. So the antiderivative of x over 2 is going to be x squared over 2, which becomes x squared over 4. We're going to evaluate there at 0 and 10. So here we get 10 squared over 4 minus 0 squared over 4, which just becomes 10 squared, which is 100 over 4, which is 25. Okay, now we're not done yet, because we are looking at a context of this integral. Context based on objects with units. So what are those units? We saw that rho, in this case, is grams per centimeter. The change of x is a centimeter. So in the integral, we see that as well. Rho is grams per centimeter. Change of x is centimeter. So the centimeters here cancel out, and our mass is in grams, which we may have expected. All right, well, great work going through this first example.